But we are going to cover some things that I think are relevant to the discussion that you were just having, which is when do you use silica fume and when do you use, when might you want to use other positives? And really the key comes down to when you need particular types of performance, you should be tailoring the binder composition to meet that performance criteria. We could talk about figuring out how little binder you need. There's many mixed design methods that are very effective in reducing the required amount of binder, but the binder itself has necessary properties. And so we're going to talk about some bridges built in really nice conditions. This is an artist's rendition of the extradosed cable stayed structure that goes across the St. Croix River, a scenic waterway in Minnesota on the left-hand side of the photograph, and Wisconsin on the right-hand side of the photograph. And about right where that truck is, to the left of the photograph, you have to pay sales tax on the concrete. On the right of the photograph, you don't have to pay sales tax on the concrete. So it became very important to determine where the concrete was going because you had to pay sales tax or not, depending on which state you're in. And it looks very nice, and this is, of course, what the politicians and the members of the DOT and the scenic waterway committees would see, but this is really what we were all trying to do, right? So we said, hey, Len, I got an idea. Let's go build a bridge between Wisconsin and Minnesota, and let's do it in the winter, because anybody can do it in the summer. That sounds perfectly good. And these are the piers rising up out of the ground, and you might notice there's something strange on the pier. There's some form, but there's also a concrete truck. Now, those of you who, and I can't imagine you don't already know this, but there's a different culture between the state of Minnesota and the state of Wisconsin. They fought it out. In fact, I don't know. I know on Sunday they played a football game because the flight coming to Boston out of Minnesota had people wearing Green Bay Packers hats and other people wearing Vikings hats. I waited for the fight, but nothing occurred, much to my disappointment. But the big difference is not only is there a sales tax on concrete in Minnesota, but not in Wisconsin, the direction in which the trucks discharge becomes important. In Minnesota, we like rear discharge trucks, and in Wisconsin, they like front discharge trucks. So you can tell which side of the river things are coming from. But depending on the orientation of the truck, this is very important. And of course, performance-based specifications have been around for a very long time. This is an ad or a cartoon from a Canadian magazine, which is why we have references to Commonwealth things. But it is a performance-based specification, right? I want your concrete should pour like Niagara Falls and should gain strength like the Rock of Gibraltar. So, pretty good. You know, you can tell which one is the contractor because he's smiling, and the ready-mix guy saying, what the hell are you talking about? But and of course, when this cartoon was made, the only way to do it to change workability and for that matter, strength really, was to change the amount of water. The water to cement ratio, and we know that it only works in one direction, right? Like time travel, they say that time travel is impossible because, while time may not necessarily only have to move forward, entropy certainly does. So we know that if we add water, we affected both workability and strength. But that's not where we are today, right? We can make all sorts of changes to our concrete. And so we had a specification that was very much performance-based. There was very little guidance given as to what material should be present in the concrete. So do we need to have a minimum cement content? Are there any limitations whatsoever on the composition of our binder? We don't have that either. There's a bunch of criteria: pump, air, press strength, hardened mineral analysis, parallax, tensile resistance, cadence, variability, modular elasticity, alkali-silica reaction, a whole bunch of tests that all needed to be run. And the specification also has the ultimate statement of performance-based specification, which says that the concrete shall be provided, designs provided by the contractor, to show a 100-year design life. But whatever that means, because that's about all the definition you're going to get. So we do some mathematical modeling, we do a bunch of things, and then of course the structural engineer also says, hey, we need a bunch of requirements for strength, and so we have superstructure is a 6,000 psi at 28 days. The precast, cast-in-place elements and external struts, they need to be 8,000 psi. You can wait for 56 days for those. And then the superstructure precast elements need to be 9,000 psi, but you can wait 90 days for them. And in fact, the specification, and you can tell by the crude nature of, for this is a slide, a picture of the specification itself. And it says, you shall obtain the strength for no more than 56 days if you use cement replacement with fly ash, slag, or other cementitious materials. I hadn't heard of cashew hoe ash, but I'm not surprised, right?
That's the new one. It sounds good. The cashews must have a bumper crop or something. How are we going to get rid of all of this? I had the great fortune as a young man of working with John Bickley. And so I learned a lot that binder doesn't have to, in fact, shouldn't just be cement. But it says, however, there's always however is one of the great words. You can wait 90 days, but you have to pay attention that fall first removal, stressing, all sorts of other things must show that that you are going to be able to construct as required. And it's pretty straightforward. The contractor read this and said, well, that's nice, but my transfer girders, the top of these piers, 85 feet off the river, they need to be post-tension in 18 hours. And in 18 hours, they only need to be 4,000 psi. Now, they need to be 8,000 psi. You got all 56 days to wait for that. That's fine. 4,000 psi in 18 hours. And the segments will be the same. So we have a bit of a problem, because the segments are being precast, and then they're being lifted in place. And those precast segments have internal transverse force tensioning. It needs to be done very quick. There's no problem. You can use any admixtures, any sublimation materials with your binder, and you have 90 days of these strength to flat. If it's 4,000 psi in 18 hours, Rocco and Bruno over here, they're going to come visit. So I was thankfully out of the ready-mix business at this point, but we were running all of these mixes for them. Specification has a bunch of other things. This is my favorite. Not only do you have to have 18 your carpet has to be released for 240 minutes. You see some stroke there, 240, written 180. 180 minutes. So why would you want, with St. Croix, the crossing is just outside of metropolitan Minneapolis. Why would you want something to set that long? And that's because of the construction method that had been selected. This is the tour company. You take a tour of the St. Croix on our glorious barge, and each of those buckets has been filled on the shore with a complete load of concrete. That is, then you can see the crane is picking it up and putting it into that hopper that's flowing into the pump that's pumping the concrete in place. So our insurance, or Semstone's insurance company, was not particularly keen on putting a whole bunch of ready-mix trucks on a barge and then floating them out 4 or 5 or 6 or 7 times a day. So this is what we compromised with, was just having a pump that was, you can see the pump is slightly raised up because it's bolted to that barge and it moves around. And so you're not able to adjust mixes out here if they're starting to need a little bit of superplasticizer. The mixer function in those buckets is pretty bad. As I said, this is the tour company go on a tour of the construction site. This is what it actually looked like most of the time, because of course we don't want to be erecting the segments in the winter, but in order to do that, we have to have built our structure all winter long so that we can erect the segments in the summer. Someone should tell Poseidon Barge what Poseidon liked to do to boats. Perhaps they should change the name. If you can see that it is a relatively complicated
piece of construction. And one of the things that this really demands is a lot of performance for the concrete. So they didn't tell us to use a retarded They said hold the concrete in a plastic state for 240 minutes without any significant change. It's something we've done before with MnDOT, so we weren't particularly frightened. And this is our mixture proportion for the superstructure. This happens to be for the 8 KSI transfer girders, which we'll talk about a little bit more. And you can see we're using a relatively mild, what is that, 350, 520, 660 pounds of cement, not cementitious material, relatively reasonable water to cement ratio at about, but I think it's about 0.33. And you can check the actual math, but I'm right. And we have 20 pounds of silica fume. Now, if you remove the 20 pounds of silica fume, we've done that other mixture many times, 6,000 psi all day long. We needed something to give us an initial set and early strength gain and heat, because we are activating the slag with heat. Those of you who are familiar with the chemistry of the pozzolanic reaction will notice that I am not using the slag at all for its pozzolanic properties, because by the time it gets reacted, all the calcium hydroxide, the vast majority of the calcium hydroxide that has been produced will hopefully have been consumed by the silica fume. And then, in fact, is how we had the work done. We also have a particular blend of Class A aggregate that was crushed, custom crushed for the project, because of the advantage of having your own aggregate sources, and it is very well graded, with the exception that there is a gap at the half inch. We like gap graded mixtures because we can pack them together. The cool kids call them tarantula curves, but gap graded mixtures, if you can control them, they pack together very nicely. And the goal here, the mix is designed to have as little cementitious material as possible, meeting the other requirements, because of course shrinkage is one of our requirements. And the way that it works is we develop that job mix formula just like it's asphalt, because we're using another facet of asphalt, the voids in the mineral aggregate. And that void in the mineral aggregate is the necessary paste. Until you have the voids between the aggregate particles filled with paste, it doesn't matter. And after that, you need a little bit more paste to get things to slip by one another. You can use a soft shell, hard core packing model to predict it, or you can very quickly get into the lab, do a bunch of dry rotted weights, which are now called bulk densities, and we go ahead and find out how much volume there is when we pack the material together based on the aggregate gradation and the relative proportions. And we then have some limits, and we control all of that. And we had developed just a few concrete mixtures. The comments for those reviewing is that we could not read slide. But the purpose of this, of course, is looking at the number of test requirements, not what they individually are. We have some conflicts. We have a conflict between the gradation requirements that we set, which deviate well outside of what MnDOT is used to seeing. The slump, which we don't care about because we the 3:3 water cement ratio and 240 pounds of water. We are using our best friend, polycarboxylate, and constructability, because if you look at these concretes, they look very harsh, very rocky. If you look at them on paper, right? If you look at the mix design, it looks really rocky. It pumps like a dream because we developed our model developed our mixtures from packing model. We also have high early strength. I forgot to mention the transfer girder. They're 8 feet by 8 feet by 75 feet long, so they're also mass pumped. So and 4,000 psi at 18 hours. So it's no problem. There's thermal requirements. We have to worry about diffusion coefficient. We have to worry about shrinkage, and we worry about cracking quite a bit. So we have our own acceptance criteria. We measure the resistivity of the concrete at about 2 hours, the surface resistivity.
And then we monitor things with resistivity, and that's our quality control check, because the diffusion test takes 56 days to run, only to find out you have the wrong concrete in the wrong forms. And I learned as a young man from John Bickley that 3 days is too late to learn that you put it in the wrong forms. And there's lots of failure modes. We could fail because we don't have a good air void structure. We could fail because we have problems with our freeze-thaw. And then the ASR interpretation, like a lot of agencies, the sort of Department of Transportation considers the ASTM 1293-1567 partnership to be a definitive test. So you go back to their origin when they're CSA 23.2, I think it's 16 and 17A. They're really screening tests. You can't fail. You can only pass. You can pass or go on and do some more. So let's focus on three mixtures: the footing, the cross beams, and the cross beams on the extradosed pier. So footings were relatively small pieces of construction, as you might imagine, as are the cross beams. There's nothing really to worry about here. We have there's a few shear studs just in case there's some wind shear going on, because the transfer girders are up there, and this is one that is under construction. And you can see it's very pretty. And we have some ready-mix trucks, but they're not the blue Semstone ones. These were ready-mix trucks owned by the contractor so that they could do a little bit of work. But all the concrete that is being brought out into the middle of the river is being brought out on barges and is to be controlled in terms of its set. So we can look at these three mixtures. We have our mixture for the footing, cross beam, and the cross beam on the extradosed piers. They range between 26 and 17% Portland cement, and they're between 3 and 4% silica fuel. We don't need anything more than that unless we don't like the finisher. Like the finisher, like those guys wanted, yeah, go with 12. But anyway, we understand that there are problems that can be associated with using silica fuel concrete. If you at very low doses like this, there's lots of silica fume people in the room. What does a silica fume act like at 3%? Like a water reducer, right? So if people say, oh God, you can't put silica fume in concrete, well, you can, just don't put 12% in. So we do a lot of this thing. You can see the diffusion coefficients are quite low, particularly for the silica fume containing mixtures. And that's, no one wants to repair these structures, and besides there's the ambitious 100-year design life with no direction, so we had to design that. And this is our compressive strength gain. And you can see the footing that is about 540, has a 90-day strength, this is cylinders now, 90-day strength at about 8,000 psi. The cross beams respectively, with additional silica fume and less Portland cement, we are getting they were getting, well, 12,000, just a little under 10,000 at 90 days in the lab. But we're also getting 4,000 or 3,000 psi at 18 hours in the lab. And this is where we dealt with MnDOT and said, listen, the issue here isn't what the cylinders break at. Who cares? You're not going to post-tension the cylinders. The issue here depends on how hot are these members and what's their maturity. At a clock time of 18 hours, how mature are they? So we built a maturity model, and with that maturity model, we were able to predict what the strength would be and then confirm it using max cure cylinders. Now, MnDOT requires you to update your maturity model every 2 weeks. Increment, right? Small steps. So we'll see. It's only been around. What Nursall did the work, Terry, in the 50s, right? So we're not sure. After it comes up to a century, we might be okay, but they're never sure. So, and we have some requirements for mass concrete, mass elements. You have we have built this performance base. This is work we've done with MnDOT, that we can handle much higher temperature differentials as our strength goes up. And we still don't, even though I doubt there's enough etringite in there to make any kind of problem, even if it was delayed at a very small cement content, so we are going to not exceed 160 degrees, because, as we saw in the picture, we are building them up above the river. So here is
here's some data that shows you our predicted model for temperature, our actual model for temperature, and our models for differential. This mixture is in conformance. This one happens to be a pure base. I didn't I didn't have, this is not a cross beam, but it could easily have been. But you can see we have a temperature rise only of about 75 degrees in a member that is 4 feet in thickness. So we're also our peak occurred faster than we anticipated or predicted, and it is dropping faster, and that's because we use the same type of approach that you would conceive for a load resistance factor design. We increase the heat over what we think it's going to be, and we decrease the heat capacity of the concrete, thereby making it more sensitive. And so we then design and say if it's going to work, we have an adequate safety factor. So you can see it feels fairly old. Again, this is the cruise line. In fact, it has a cruise boat down on the bottom. And you can go and visit the structure, and here it is under construction at some point. And this is when they wanted people to tour it, but this is when we were building it. So, not a lot of tour boats coming out on here, but the interesting thing is that the only reason that you can move the barge around those piers is because Lunda, the contractor, has an icebreaker out there breaking up the ice. So in case you want to visit Minnesota, February is the best time to go. Now, of course, even if you're born to do engineering work, things can go wrong. And we had a particular problem with one of the placements. This is a scanning electron microscope of our binder. We can't see the silica fume, but we can see everything else. You can see the round fly ash, you can see the relatively coarse-grained slag, and the nice fine-grained cement. The reason that we're looking at this is because we're determining how much additional hydration potential there is. And we think there's a lot. As you can see, most of those grains have done absolutely nothing. This is what happens when we tell you put on a big blanket, and then you say, well, we did, but then it blew away, which can happen. We also noticed that we had some issues with our strength depending on which fly ash we were using. Due to supply issues, we protested and said they should stop. But look at what happens to the early age or the middle age strengths when you switch from portage to coal-free fly ash. So these are basically cubes being cast in a lab. But we were able to resolve this, and we're able to show for MnDOT that even though we haven't met the strength, all we need to do is enclose and heat, and we will meet the strength as long as we don't dry it out. We've also done this on a number of bridges. This is the I-35W structure under construction in Minneapolis. It has a little bit of silica fume in some of the mixes, but this is looking at rapid chloride permeability over time. And this is why with things like silica fume in conjunction with slags and fly ash, you're better to look at 90 days. The results are very low, and if we hadn't been tracking the resistivity, we probably would have thought that they were unreasonable. Strengths are always pretty good. And we have done some, like everything else, you have some problems, and one day they said there appears to be an anomaly in the cross-hole sonic logging, so we took a core down a depth of about 75 feet, and the shaft at 21 days, mass concrete, 8-foot diameter shaft, the cores were breaking just over 10,000 psi. The 28-day strength lab cures were only 5,500 psi. And this is the greatest advertisement for why you should not rely on the cylinders for purposes to which they are not intended, one of which is to determine in situ strength, right? The purpose of the cylinder is to obtain the strength that has been delivered to the site. This is another small quantity of silica fume containing structure here at Lowry Avenue Bridge, and this is a little bit of reinforcing steel, and it gets placed by leaving the form open to this point, filling it up to this point, and then going on and filling the rest of it. But what's nice is when you use slags and you use these mixtures that the water cement ratio is very low, you can have it pour like Niagara and have strength like Gibraltar. This is the structure as it looks, and this is a self-consolidating concrete, but self-consolidating concrete isn't magic. This is a reinforced concrete structure in Canada where they felt that the SCC was magic and you can drop it from any length. They just didn't talk to the structural engineer. So this concrete where all of the ties are coming together, some bundled bars and stuff, it's pretty hard even for self-consolidating concrete to get through that, so you need to pay attention. Thank you very much for the time, and hopefully I've got you back on track. I see Julie is here, so